I'm Lori DeToro, Senior Communications Manager for Turntide Technologies. Thank you for joining us today to learn more about hybrid architectures for commercial vehicles. We are thrilled to have Head of Product for High Performance Motors, Matrishvan Ravel, presenting for us this morning. Thanks so much for joining us, Matrishvan.
Thank you.
Before we get started, as usual, I will go through just a little bit of housekeeping. Before This presentation is being recorded and will be available on demand on the Current and Wave website. We will be taking questions at the end of the presentation, so please use the Q&A section, not the chat, to ask your questions anytime during the webinar, and we'll answer as many as we can before the end of our time. You'll also see in the chat a link to register for the July webinar, which will be around the value of a strong applications team with any partner that you're working with. Feel free to register for our next one. Also remember that this is a live event, so when we mess up, like I did just a minute ago, laugh along with us. And that is it for housekeeping. Matrishvan, please take it away.
Thank you, Laurie. Thank you, everyone, for making the time to attend the webinar. Today, I want to be discussing about how axial flux motors are helping power the shift to hybrid vehicles, especially in the commercial vehicle sector. Let's go through what we'll be going through in our webinar. One of the first things that I want to tackle is around the decarbonization challenge. Regulation-wise or not, there is a decarbonization challenge that's been put on various OEMs, and that varies by geography. There's varying levels of decarbonization regulations in Europe and USA, and as the political winds move, those tend to change as well. So that's one definite pressure, but we'll explore how that is prompting a move to more sustainable hybrid vehicle architectures. And then there's the other aspect of it being commercially viable. No matter the amount of regulation or the stringency of the regulation, unless it makes commercial sense, the OEMs will always prefer an existing solution over investing in new sets of solutions. So I want to explore how by moving to a hybrid architecture, it still makes commercial sense. And that's where the total cost of ownership and return on investment piece comes into play. I want to explore how we can reframe the decision of whether to go into a hybrid architecture or not, and how best to blend the mechanical and electrical torque powers in a commercial vehicle application to give the best results. Now, one of the things that Turntide has been focusing on very heavily is axial flux motors. And it just so happens that they tend to be very well suited to moving to a hybrid architecture. So we'll explore the physics behind that and why that is extremely suitable for moving to hybrid architectures in CV space, and what are the benefits that come with moving to an axial flux motor architecture, and how that helps you address various thermal, mass, volume, and packaging challenges that come in the commercial vehicle space. We'll also look at various architectures that are possible within a hybrid system, whether it's series, parallel, or a new type of architecture that we are seeing evolving, which is a multi-flex architecture, where it's the best of series and parallel all in a single package. We'll look at some real-world application examples and also see its applicability and versatility, not just in commercial vehicle on-highway applications, but also off-highway and more challenging defense-related duty cycles. And finally, we'll take a look at how it has various serviceability, total cost of ownership, and ROI benefits. As usual, if you have any questions, please feel free to put them on the meeting, and we will address them as we go through and right at the end as well. So, as I've said, there's varying levels of decarbonization rules. For example, if you're in the North American territory, there are various CARB regulations, or California Air Resources Board regulations, that are prompting freight and commercial vehicle operators to move to either a fully electric or a hybrid architecture. In Europe, there are set timelines which are, more recently been a bit diminished, but there are 2030 and 2035 timelines towards a full decarbonization as well. Now, regardless of the timelines of the regulation, the constant question that I see when I go to commercial vehicle customers of ours is, does it still make economic sense? And that could only be so if there is some sort of total cost of ownership benefit. Um, the the decarbonization squeeze is made worse by gaps in charging infrastructure. It's well known that the charging infrastructure is still in its nascent stage. It is ever evolving, but still not enough to service a 100% full-fledged move to BEV or hybrid architectures. Where it does exist, it's often very expensive and not very reliable. And the duty cycles that you see in commercial vehicle world, especially on long routes, are very demanding. You'll see high rates of transient torque responses, things that demand full torque, and a long range every shift across the year. So the question comes, how can vehicle design and component selection help us overcome these challenges? So a natural solution is moving to a hybrid architecture. Now, the choice of components that you have in hybrid architecture can make it either a best of both worlds or worst of both the worlds solution. And we'll look and see how to make it a best of both the worlds solution by choosing the right componentry and design. Um, So when you blend electrical and mechanical power through your ICE powertrain and an EV powertrain in a hybrid mode, you need to blend the torque across every operation, be it regen, be it braking, be it torque transients. You also need to meet the response targets. EV powertrains will be much more responsive, but then you need to balance it with range as well. So you need to be operating at the right efficiency point on your torque speed curve to make sure that while meeting fast transient responses, you're still operating at the most efficient point. And last but not the least, there's extreme range requirements for every duty cycle. All of this has to be met while staying within the overall strict mass envelope, a strict volume envelope, all the cooling requirements and serviceability requirements. So it's a multidimensional problem, and you need to solve it with a component and design selection that meets each of those criteria. So one of the solutions that we've found very useful in real-world examples to meet all those challenges is an axial flux motor. Now, let's just look at what an axial flux motor is. It's all about the geometry. The magnetic flux, or the direction of the magnetic flux in a conventional radial flux motor, is radiating outwards from the axis of rotation, whereas in an axial flux, the magnets are arranged so that the magnetic flux is along or parallel to the axis of rotation. That magnetic arrangement gives it the characteristic flat pancake shape rather than the long cylindrical shape that the radial flux motors have. And it is this geometry, the ability to fit in a high amount of torque in the small space, that leads to all the advantages that result from it. Looking at the physics of the axial flux motor, it's all about a ratio that we call the D to L ratio, where the D is the diameter of the motor and L is the path or the length of the magnetic flux path. If you have a shorter magnetic flux path, your torque delivery and therefore the efficiency rises. And the D, the diameter, is representative of the amount of magnetic material that you have in the motor, and your flux strength would basically climb, your field strength would basically climb as a particular function of the diameter. If you maximize your D to L ratio, that results in a higher efficiency and a higher torque yield. And if you look at the form factor of the radial flux motor versus the axial flux motor, the radial flux motor is large in diameter and small in the flux path length, the axial length, giving you a much higher D to L ratio, whereas the radial flux motor tends to have smaller diameters, much longer flux path lengths, and therefore a lower D to L ratio. So wherever the geometry of your powertrain allows you to incorporate an axial flux motor, there's always a net advantage in terms of the torque and the power delivery. So if you look at head-to-head in comparison between a radial flux motor and an axial flux motor, the radial flux motors have a long cylindrical can shape. The axial flux motors tend to be flat, compact, pancake type. The D to L ratio difference between the radial flux and the axial flux motor actually benefits the axial flux motors, and you tend to have 2 to 4 times higher torque and power density delivery. The the torque delivery varies as per the cube of the diameter in an axial flux motor, whereas it varies with the square of the diameter in a radial flux motor. And if you plot out the two curves, the cubic and the square law curves, you'll have greater divergence as the diameter grows between the cube and the square wave functions. And therefore, you end up having, for a reference baseline design, typically 2 to 4 times higher torque and power density delivery in a axial flux motor. That also translates into a lighter low inertia design of the rotor, and you have typically a better power to weight ratio. The axial flux motors are half the weight, typically of a equivalent power radial flux class. With the right electromagnetic design, you can also ensure peak efficiencies of up to 96% or a percentage value that is in exceedance of the IE4 efficiency class. Um, the geometry advantage of the short axial length means that if there's a tight bay, um, think of a commercial vehicle chassis, the powertrain bay, if it's very short and tight, the axial flux motor would still fit in, allowing you to electrify the platform. Whereas if you were to replace it with a radial flux motor, you'll have to change the chassis design, or in some cases, it's not even possible to fit in a full radial flux motor. Much lesser use of active material, so very much optimized when it comes to iron, copper, and even magnetic material use in the axial flux motor. We'll also cover a topic called cogging torque later. The axial flux motor with the right design choices can lead to much smoother NVH profiles as well. So these are some of the benefits that you get by moving to an axial flux architecture, provided the space claim is constrained and there is an inherent advantage in moving to one. So yeah, that's the first advantage I want to discuss. You can very easily drop in an axial flux powertrain without the necessity to redesign your powertrain chassis. It can easily integrate into existing diesel and hybrid platforms with minimal packaging changes. It's already 50% lighter. So whether it's used as a standalone motor or integrated into an electric drive unit or used for power takeoff applications, the volume taken up by it is almost half of what an equivalent radial system would take. Um, and the systems that Turntide has designed, they come with multiple mounting shafts and interfacing options, which follow various ISO, SAE, DIN, and other industry standards. So, we've used the design of the motor to be able to interface with it very easily and quickly. So just looking at some figures, we are able to see a typically 18.5 Newton meters per kilogram specific gravimetric torque density and a 6.8 kilowatts per kilogram specific power density on our 430 double stack motor, and a peak efficiency of 96% plus, or IE4, which is the highest defined industrial energy efficiency standard for electric motors. These motors are also scalable, so you can either increase the diametric range or also stack them one after another, giving you flexibility in both the radial and the axial dimensions within a powertrain. So with stacking, a system anywhere from 55 kilowatt to a megawatt is possible by flexing those two parameters. Now, I cannot stress enough the efficiency importance across various duty cycles. You need usually a fairly high torque capacity, especially a peak torque capacity, if you want to regenerate every bit of the braking torque. Axial flux motors tend to have a large delta ratio between the continuous torque and the peak torque. Typically 2.5 times of continuous torque tends to be the peak torque, whereas in case of radial flux motors, it's more like 1.5 to 2 times the continuous torque. This delta, especially for water-cooled system, means that for heavy braking applications, you tend to get much better regenerative capacity from an axial flux motor as compared to a radial flux motor. Another key thing that this allows OEMs to do is downsize their engine. So the presence of a torque boost or a range extended function from an axial flux motor allows the OEM to downsize the engine. I've got various use cases and examples where turntide motors have gone in, helped reduce the existing diesel or petrol engine on a hybrid system, which has led to a virtuous cycle of various other benefits as well. Um, One of the biggest problems from an emission point of view is idle state of the engine. Um, Being in hybrid systems allows you to get rid of the idle state altogether. Any wasteful engine idling at stops or low load can be removed. You can just be in an electric mode at that time. All of this, coupled with class-leading 96% efficiency, means no matter what part of the duty cycle you're in, be it regeneration, idle, or peak performance or continuous performance, you can get efficiency and range benefits in all of these stages. So let's come down to the money clincher. One of the constant questions that I get from OEMs is all of that is great, and we might even be able to justify incorporating an axial flux motor into a powertrain, but how do we sell it to our customer if it comes at a price premium? And the answer is TCO benefits. So you usually have at least 15 to 20% real world, real life total cost of ownership benefits from a fuel use point of view. And these are actual figures that we've seen performed and benchmarked using our systems on-road diesel consumption platforms. It is, however, fuel agnostic, and it applies whether it's a petrol platform or a diesel platform. Um, the way you blend the torques here is you need to make sure that the engine is running at its most efficient load point while the motor covers your transients and peaks. If you're using it in a range extender function, that onboard generation basically extends your range without having to depend on roadside fast charging. So if you're having long haul operations where charging infrastructure is next to non-existent, then the range extender functionality allows you to charge up your battery systems during normal operation without having to rely on a dedicated charging infrastructure. And coming to an obvious environmental benefit, your electric first operation, your idle elimination also helps you to cut NOx and CO2 emissions, especially in your urban stop and start duty cycles. Um, the key point that makes the axial flux motor suitable is speed matching. So whether it's a diesel engine or a low speed petrol engine or a high speed petrol engine, we have specifically designed a series of motors that are exactly speed matched with the best optimum efficiency points of the ICE engines. So our largest diameter class series, the 430, is speed matched with diesel engines where the ICE engine optimum range of 1500 to 2000 RPM is matched with a motor base speed of around 2000 RPM and the max speeds of 3500 to 3700 RPM. With low speed petrol, the speed range is a bit higher than diesel. We have a smaller diameter class called the 400 series to match that. And for high speed petrol, we have the smallest diameter class of the 300 millimeter series, which is speed matched to that. This speed matching is what allows a smooth torque blending to occur and make sure that, be it from an engine perspective or from a motor perspective, you're always running at your maximum efficiency points. This is, if there's one thing that you can take away from the presentation, it would be this: is the speed matching that allows for the highest efficiency to be eked out of the powertrain. All of this has to still match fairly stringent constraints in terms of thermal limits that the vehicle would go through, um, strict mass limits, strict weight limits that you want to impose onto the vehicle design so as to enhance your range again, um, and make sure that structurally and from a finite element analysis perspective, it is all suitable and you'll still have a long life despite having a fairly ruggedized operation of the motor and the vehicle. All of this can be done with the right set of thermofluidic optimization, optimization of the cooling channel, making sure that we're using the right material in our winding insulation and our cables to withstand those high temperature or extreme temperature operating environments. Within the hybrid architectures, you've got two mostly popular existing architectures, which is your series or range extended one or a parallel hybrid architecture. In a series hybrid architecture, you'll have the internal combustion engine coupled with a motor generator, which then produces your um, power generation. There is a battery that's being charged up, but there is no mechanical link between the engine and the wheels. The, the system is purely used for power generation, and then there's an electric drive that follows. Um, this is typically the cleanest way of separating the torque blending operations and is usually the most popular. However, there are use cases where you don't want sole reliance on battery. So both from a reliability perspective as well as ability to go to higher torques or higher ramps in case of demanding. You want to combine the torque of the internal combustion engine with the motor to produce a much higher overall torque in a parallel hybrid system. And the wheels can basically be either jointly or independently driven by the ICE component or the motor component or both. And the third, more recent and evolving architecture that Turntide has been pioneering is a multi-flex system. So you can switch modes on demand. You can have intelligent electric clutch actuations to basically move from a fully series to a fully parallel to a both architecture. So in the same vehicle frame, without having to change any platform variation, you can just by intelligent actuation move from a series system to a parallel system or both. So the single motor, the axial flux motor, can very efficiently do all the four jobs. It can do your traction at the right torque levels. If you want a torque boost, that can be provided from the motor as well. It can capture a very high regenerative force because the peak to continuous torque ratios are much higher. And it can be used either as a generation or as a power takeoff mode. So one of the use cases that I like to refer to is the use of our motors in commercial trucks and delivery fleets. This is an example of a customer who has basically matched our motor series with their vehicle class across a commercial vehicle fleet. So our smallest motor with a 73 kilowatt continuous power is being used to power their 12-ton system. A slightly larger motor is being used to power the 19-ton GVW system, and one of the largest double stack motors being used to power 33 and 55-ton commercial vehicles. And there's been an observation of at least 15 to 20% fuel reduction for a real world duty cycle. And this also makes it very retrofit friendly. They haven't had to redesign their powertrain or their vehicle for that matter. And simply by downsizing the engine and introducing the pancake shaped axial flux motor, they've been able to achieve this. So, been able to achieve best of both the worlds. And there are many other use cases where you don't have charging infrastructure availability, construction and earth moving being one. Um, it also experiences demands for very high torques, severe temperature operations, and doesn't have the luxury of space. There's so many implements that are used in construction and earth-moving equipment that space is a luxury, and the axial flux motor is an easy and natural fit into that environment. Um, Another growing application area for us is defense. So defense platforms tend to require stealth capability. So they do want a mode where they can switch to electric motor only operation and reduce the noise signature of the vehicle, so as to have stealth capability in defense operations. And again, similar challenges are faced in those areas as well. They want very high torque throughput spaces at a premium because of the amount of equipment on those platforms. And the axial flux motor and its derivatives are a natural fit there as well. Marine and all-terrain vehicles are also an interesting application area for us, both from a generation, propulsion, and ruggedness required for all-terrain operation, as well as the speed matching in case of marine diesel engines as well. You couple all of those benefits with a high lifetime, and you usually have a winner. We have Our design philosophy has been to not require frequent servicing of our motors, to the point that we've designed the motor to have such a long lifetime that it's a constant use case without having to have any serviceability intervals. So we have validated product lifetimes of up to 50,000 hours on various real-world reference duty cycles. Um, that is impressive in terms of reducing the serviceability bill of the OEM. In case of hybrid systems, there's also reduced engine degradation because you're running the engine at its best operating point. There's much lower wear and tear. There's much less unplanned downtime. And the range that we have allows us to have integration in a fuel agnostic manner. So there is a product that is matched with every type of ICE powertrain. A very proud example of us has been our semi-integrated axial flux EDU. So we've been able to provide a semi-integrated EDU with the power electronics, the motor, and the transmission gearbox for use in various all-terrain vehicles, recreational vehicles, and off-highway vehicles as well. And the motor inverter have a shared cooling system. There is an existing 50 kilowatt to 40 kilowatt uh, range that's available of continuous power that's available, and it's got scalability to higher power ranges as well. If you're not familiar with the power takeoff system, it's usually, if you imagine it as being the opposite of generation. So in a generation system, in a generator system, you're using mechanical power to generate electric power, but the use of an electric motor. With a power takeoff, you're using the motor inverter system in the opposite direction. You're using electric power from battery usually to do some work function. So if you imagine work trucks or trucks with cranes or hoists or cement mixers or anything of that sort, they will require uh, the actuation of mechanical power to happen from stored electric power in case of electric systems. And again, the axial flux motor and inverter combination that we have is very much suited to deliver the ePTO system. This also gives you, in case of hybrid systems at least, an idle-free operation. If you're using a pump-mounted actuator, you can easily vary speed and flow requirements purely from an inverter control point of view. And the system efficiency is at a very high and impressive 90% figure. Um, you can have that in an ePTO system. You can have full torque from an ePTO system at 0 RPM. So if you have an engine-driven PTO, a mechanical PTO, the engine must get to an idle state, whereas the ePTO gives you immediate hydraulic power at 0 RPM. and your performance is basically decoupled from your engine performance. Pump speed and flow are completely independent, and the control for that is completely independent of your engine speed. So you don't need to vary your engine speed in order to get higher EPTO performance output. Very high system efficiency, as we touched on earlier, and a very quiet idle-free or engine idle-free work environment. So it reduces your noise, it reduces your fuel use in case of hybrid systems, and overall wear and tear as well. So if there is nighttime operations or urban operations that are required, then an EPTO is an ideal choice that can meet all those criteria. And in case of work trucks, similar to commercial vehicle fleets, it's the ROI that is the most important metric that fleet operators are looking for. And eliminating this, eliminating the engine idle operation and reduction of wear and tear is giving the fleet operators a very fast payback. You can have various applications of the EPTO architecture as well. You can have a direct drive hydraulic, as we discussed before. You can have high peak stationary operation as well. And it's been designed such that it can have multiple output interface options, whether it's direct pump mount or ISO splines or DIN flanges in terms of outputs. So yeah, it's useful in construction and earth moving equipments, compressor, pumps and compressor applications, municipal trucks, refuse collection, cement mixers, various body hydraulics as well. We have an existing range of EPTOs moving from 50, 100, and 150 kilowatt, and that the multiplicity of the power classes is due to our wide range of electric motors that have been designed across those different power classes and are compatible for operation between 200 to 850 volts. This is a production-ready semi-integrated system with our axial flux motor and our high voltage inverters. And this is proposed for use as an electric PTO. And it's built on the maturity that we have achieved through series production of our motors and inverters. So what are the key takeaways that I want the audience to take from that? The main decision is how to blend your electric and mechanical power while staying within the overall requirements of the system. Geometry of the axial flux motor is what's giving you the advantages that you need to make that work. With high efficiency operation and the right matching into hybrid architectures, there is a very quick path to lower TCO and higher ROIs by reducing your fuel use by 15 to 20%. The speed matching is what's giving a refined and seamless power delivery. It's applicable even when there aren't any charging infrastructure availability, and it has a very low lifetime cost and high MTBF in terms of useful life of the product. So that's what I want to leave the audience with. I'm happy to take any questions now.
Fantastic, Patricia. Thanks so much for that great conversation, great presentation. We have a couple questions. You can ask more. Go ahead and get them in if you have them. The first one is, for the motor in the EDU, what is the cooling system? How do we
It's
cool
a
it?
standard water ethylene glycol mixture that's being used for cooling on the
Okay.
motor and the inverter system. Usually
And
50-50 veg.
okay. And if someone is wanting to retrofit an existing design, with the system you've talked about, what are some challenges that might occur? What types of is there anything that would challenge an application of this in a retrofit?
Perhaps the biggest consideration. So as far as the space is concerned, we've seen that we are able to deliver the right power level within a very short space. And I wouldn't say it's necessarily a challenge, but the biggest work item or the work um, that you have to do while retrofitting is your mechanical interfaces.
Okay.
So if you're able to specify and standardize those mechanical interfaces as much as possible, it makes the overall integration a lot quicker. We've had examples where we've turned around a retrofit on a classic car within a 6 to 9 month period, whereas typically those sorts of developments take more than a year. So yeah, if you're able to standardize your mechanical interfaces, that's a much quicker route to integration in retrofits.
Okay, well, I'm not seeing any other questions coming in, so that is all we have today. Well, two more just popped in, so I'm gonna. What is the cost premium of an axial flux motor versus a radial flux motor, if you can
I knew
answer
this was
that?
going to come. I knew this question was going to come.
Doesn't it
So
always?
it does. It's a usual question. So axial flux motors historically have been considered to be at a much higher cost premium, and the primary driver of that is the manufacturing complexity that's involved. What we've been doing at Turntide is investing heavily on automation and a design that is fully ready for manufacturing. So we've spent months perfecting our design for manufacturing capabilities and also invested a lot in automation so as to make the process as quick as possible and reducing the manufacturing complexity. That still leaves us with a slight premium of about 20 to 50% higher, but that is a premium that OEMs are willing to pay for the benefits that they're getting in terms of performance and ROI.
Okay, the next is the minimum voltage starting at 200 volts, or can I couple four 48-volt banks to make 200? Thus, my entrance remains 48-volt EU safe.
Um, if you're banking for 48 volts in series and getting it up to 200 volts, we can make that work. Yeah. So the motor range has been, and the motor can even operate as low as 100 volts. But it's typically inverter efficiency in terms of 650-volt devices that usually operate at 400-volt range. That if you go much below 200, then your efficiency starts dropping and you don't get enough useful power out of it. But yeah, if you have four 48-volt banks that you are seriesing up, leading up to an overall 200-volt system, then we can make that work.
Yeah, he clarified that said, meaning I can charge then at 48 volts instead of 200 volts.
You'll need some DC-DC conversion and onboard chargers for that to satisfy your 48-volt charging, but you'll still need to be able to provide 200 volts on the DC link to the inverter. There is a low
Okay.
voltage range that we have as well. So if your power requirements are quite low, we have a low voltage inverter range called our Gen 6 inverter, which have 48, 96, and 110 volt options. So yeah, we can explore a low voltage powertrain with our and partner motors if you want to operate the full system at 48 volts, for example.
Okay, the next one is either in prototype or production, what are some examples of applications where the motors are being used? I know we have a lot of those, so
Name a sector. So
yeah.
we've got multiple examples across the sector. So I'll probably start with commercial vehicles. The hybrid commercial vehicles across the weight classes that I've mentioned is one. Power takeoff systems on commercial vehicles as well. Range extender systems on on commercial vehicles. In mainstream automotive, it's pure BEVs and hybrid EVs, both from a, let's say, premium car perspective as well as some passenger car applications. So that's CVs and automotives, off-highway and construction. So it's been used in mini excavators, diggers, dozers, mining trucks, both for traction and ancillary applications like cooling, um, off-highway construction, agriculture,
Marine.
defense, marine. Yeah, marine, both from marines usually in a series hybrid setup. So we've used the largest of our diameter class, the 430 motor, both in the single stack and double stack as a marine generator on various boat and yacht platforms. And there's defense applications that I can't go into.
Um, so the question about obtaining the information for the low voltage options, if you go to our website and click power electronics, you'll see all of the low voltage inverters there. I'll answer that one for you, Matrish, when you can take a break. And then someone just said, what about the status of three wheelers in India?
Yeah, we have
I'm,
that's
yeah,
again for low voltage applications. So yeah, we have 48 and 96 volts applications in India. That's where we primarily offer our power electronics along with some partner motors. So yeah, those are our active projects in various stages of either series production or pre-production test. But yeah, those that's an active market that we've been supporting since many years.
okay. Well, I do
And
think,
just on that point, I
no,
must
please
add
do.
that we've been able to get class leading range on those platforms as well, and that's down to um, the motor inverter pairing and tuning and optimization, efficiency optimizations that we get from that pairing exercise. We've been able to push and extend the range on those low voltage three wheeler applications as well.
Excellent. Well, I do think that is all of our questions for today. Matricia, thank you again for a great presentation. Attendees, thank you for joining us. This webinar will be available on demand in about 48 hours. And if you can, take a minute to check the chat and go ahead and register for the July webinar, which will be coming up next month. And we hope you have a great week. Thank you.
Thank you all for your questions and participation. Have a great week. Thanks.